parallel underground installations involving 120/208 volt feeds, the grounded conductors, also known as neutrals, are considered an independent phase. This determination is critical when adhering to the National Electrical Code, specifically Section 300.20. The core principle of NEC 300.20 states that conductors of different systems, circuits, or classes of service shall not be placed in the same raceway. Applying this to your scenario, where you intend to pull these 120/208 volt feeds as isolated phases to simplify termination, it necessitates understanding that the grounded conductors also require separation. This means each isolated phase of the 120/208 volt system must be physically separated from each other and from the grounded conductors. Consequently, the implication is that you cannot simply pull one neutral in each conduit alongside the isolated phases to circumvent the stipulations of NEC 300.20. Instead, each conduit should contain two isolated 120 volt phases, designated as lone and L2, and one neutral, whether it is a shared or dedicated neutral. This segregation is crucial for several reasons, primarily concerning safety, reliability, and adherence to the electrical code. Firstly, from a safety perspective, isolating the phases helps prevent accidental contact between phases and ground. Such contact can lead to electrical shocks, posing a significant hazard to anyone interacting with the electrical system or its surroundings. By ensuring that the phases and grounded conductors are in separate conduits, the risk of such accidental contact is substantially reduced. Secondly, reliability is enhanced through phase isolation. When phases are not properly separated, there is a higher likelihood of interference and phase imbalances within the electrical system. These imbalances can lead to voltage fluctuations, equipment malfunction, and overall system instability. By isolating the phases, you minimize these potential issues, ensuring a more stable and reliable power distribution. Thirdly, and perhaps most directly, adherence to NEC 300.20 mandates the separation. While it might seem more convenient to pull one neutral in each conduit with the isolated phases, doing so would be a direct violation of the NEC. Code violations can result in fines, project delays, and, more importantly, compromise the safety and integrity of the electrical installation. Therefore, to maintain code compliance, safety, and reliability, it is imperative to follow the prescribed method of separating the phases and grounded conductors in parallel underground installations. Ignoring this requirement could lead to substantial risks and legal ramifications. The correct approach involves ensuring that each conduit contains the appropriate combination of isolated phases and a neutral conductor, thereby adhering to the requirements of NEC Section 300.20. And ensuring a safe and reliable electrical system. This setup ensures safety by preventing accidental contact between phases and ground, which could reduce the risk of electrical shock. Isolating phases minimizes interference and protects against phase imbalances, enhancing reliability. Moreover, this approach guarantees compliance with NEC 300.20. In summary, even though it might seem convenient to run one neutral in each conduit alongside the isolated phases, it is not permissible under the NEC and could result in safety hazards and code violations. Remember to always consult the most current edition of the NEC and local electrical codes, as interpretations and requirements can vary. When planning an electrical installation, particularly one involving parallel underground conduits, it is important to understand the nuances of conductor placement and the requirements outlined by the National Electrical Code. The question at hand pertains to whether grounded conductors, or neutrals, should be treated as an independent phase and therefore require their own conduit when pulling 120/208 volt feeds as isolated phases. The National Electrical Code, specifically Section 300.20, addresses this issue by stating that conductors of different systems, circuits, or classes of service should not be placed in the same raceway. In the context of your query, this means that the isolated phases of a 120/208 volt system must be separated from each other and from the grounded conductors. Therefore, each conduit should contain two isolated 120 volt phases, denoted as lone and L2, and one neutral, which can be either shared or dedicated. This separation serves several important purposes, including safety, reliability, and code compliance. Safety is enhanced because isolating the phases helps prevent accidental contact between phases and ground, thereby reducing the risk of electrical shock. Reliability is improved because isolating phases minimizes interference and protects against phase imbalances, which can lead to voltage fluctuations and equipment malfunction. Finally, adhering to these guidelines ensures compliance with NEC 300.20. B, which is essential for legal and regulatory reasons. Although it may seem convenient to pull one neutral in each conduit with the isolated phases, it is not permissible according to the NEC and could lead to safety hazards and code violations. Therefore, it is crucial to adhere to the prescribed method of separating the phases and grounded conductors to ensure a safe and reliable electrical installation. Let's delve further into the technical aspects of parallel underground installations, focusing on the specific requirements for conductor placement and the implications of NEC 300.20. B. When designing such a system, several factors must be considered to ensure optimal performance and safety. Firstly, the choice of conductor size and type is critical. The conductors must be adequately sized to handle the anticipated load, taking into account factors such as voltage drop, ampacity, and ambient temperature. Secondly, the type of insulation used on the conductors should be appropriate for underground installations, typically cross-linked polyethylene, or XLPE, or similar materials that are resistant to moisture and chemicals. Thirdly, the conduit material must be suitable for direct burial and capable of withstanding the mechanical stresses associated with underground installations. Common choices include rigid polyvinyl chloride, or PVC, or rigid metal conduit, or RMC, depending on local codes and environmental conditions. Now, focusing on the arrangement of conductors within the conduits, it is essential to understand the principles of phase balancing and neutral current management. In a 120/208 volt system, the ideal scenario is to have balanced loads across all three phases. However, in reality, loads are often unbalanced, leading to current flow in the neutral conductor. Excessive neutral current can cause overheating and voltage drop, which can negatively impact the performance of connected equipment. Therefore, it is important to minimize neutral current by carefully distributing loads across the phases and by using appropriately sized neutral conductors. In the context of NEC 300.20, B. The requirement to separate phases and neutrals in different conduits has implications for neutral current management. By isolating the neutrals, you are essentially creating multiple parallel neutral paths, which can help distribute neutral current more evenly and reduce the risk of overheating. However, it is important to ensure that the impedance of each neutral path is similar to avoid circulating currents between the neutrals. Circulating currents can lead to increased losses and potential damage to equipment. To achieve this, the length and size of each neutral conductor should be as consistent as possible. Furthermore, it is important to consider the grounding and bonding requirements for parallel underground installations. The NEC requires that all metallic conduits and enclosures be properly grounded to provide a low impedance path for fault currents. This is typically achieved by bonding the conduits and enclosures to a grounding electrode system, such as a ground rod or a metallic water pipe. The grounding electrode system should be sized according to the requirements of the NEC and local codes. In addition to grounding, bonding is also essential to minimize voltage differences between different parts of the electrical system. Bonding involves connecting all non-current carrying metallic parts of the electrical system together to create an equipotential plane. This helps to reduce the risk of electrical shock and prevent damage to equipment. In summary, parallel underground installations require careful planning and attention to detail to ensure safety, reliability, and code compliance. The key considerations include conductor sizing, insulation type, conduit material, phase balancing, neutral current management, grounding, and bonding. By adhering to the requirements of the NEC and best practices for electrical installations, you can create a robust and reliable electrical system that meets the needs of the application. Keep in mind that local codes and regulations may vary, so it is always important to consult with a qualified electrical engineer or inspector to ensure compliance with all applicable requirements. When implementing parallel underground installations, several other factors warrant careful consideration to ensure a safe, reliable, and code-compliant electrical system. These factors include trench depth, backfill material, conduit spacing, and identification. The depth at which the conduits are buried is crucial for protecting them from physical damage. The NEC and local codes typically specify minimum burial depths based on the voltage level and the type of installation. For example, direct buried cables generally require a greater burial depth than conduits encased in concrete. The backfill material used to fill the trench around the conduit should be carefully selected to provide adequate support and protection. The ideal backfill material is free of sharp rocks, debris, and other materials that could damage the conduits or cables. Sand or fine gravel are commonly used as backfill materials because they are easy to compact and provide good drainage. The spacing between conduits is also important to consider. Adequate spacing allows for proper heat dissipation and prevents the conduits from rubbing against each other, which could damage the insulation. The NEC typically specifies minimum spacing requirements for conduits based on their size and voltage level. It is also important to properly identify the conduits and cables in a parallel underground installation. This can be achieved by using color-coded tapes, tags, or labels. The identification should clearly indicate the voltage level, circuit number, and any other relevant information. This makes it easier to trace and maintain the electrical system in the future. In addition to these physical considerations, it is also important to address issues related to voltage drop and fault current protection. Voltage drop occurs when the voltage at the load end of a circuit is lower than the voltage at the source end. Excessive voltage drop can cause equipment malfunction and reduced performance. To minimize voltage drop, it is important to use appropriately sized conductors and keep the circuit lengths as short as possible. Fault current protection is essential for preventing damage to equipment and protecting personnel from electrical shock in the event of a fault. Fault current protection is typically provided by fuses or circuit breakers. The fuses or circuit breakers should be sized to protect the conductors and equipment in the circuit from overcurrents and short circuits. The selection of appropriate overcurrent protection devices is crucial for ensuring the safety and reliability of the electrical system. Furthermore, it is important to conduct thorough testing and commissioning of the parallel underground installation before placing it into service. Testing should include insulation resistance tests, continuity tests, and voltage drop tests. These tests verify that the electrical system is properly installed and functioning correctly. Commissioning involves energizing the system and verifying that all equipment is operating within its specified parameters. During commissioning, it is important to monitor the voltage, current, and temperature of the conductors and equipment to ensure that they are within acceptable limits. In conclusion, parallel underground installations require careful planning, design, and execution to ensure a safe, reliable, and code-compliant electrical system. The key considerations include trench depth, backfill material, conduit spacing, identification, voltage drop, fault current protection, testing, and commissioning. By addressing these factors, you can create a robust and efficient electrical system that meets the needs of the application. Remember to always consult with a qualified electrical engineer or inspector to ensure compliance with all applicable codes and regulations. Additionally, ongoing maintenance and inspection are essential for ensuring the continued reliability and safety of the parallel underground installation. Regular inspection should be conducted to check for signs of damage, corrosion, or deterioration. Any issues that are identified should be promptly addressed to prevent further damage or potential hazards. Maintenance activities may include tightening connections, replacing damaged components, and cleaning conduits and enclosures. It is also important to keep accurate records of all maintenance and inspection activities. These records can be valuable for tracking the performance of the electrical system and identifying potential problems before they become critical. In summary, maintaining a parallel underground installation requires a proactive approach that includes regular inspections, preventive maintenance, and accurate record keeping. By following these guidelines, you can extend the lifespan of the electrical system and ensure its continued safety and reliability.